Ladies and gentlemen, so in my last video, I said I was going to introduce you to the stack and the heap and talk more about it. However, to do this, I would like to first introduce you to the difference between physical and virtual memory. Now, this is not typically done with the introduction to the stack and the heap. Typically, it's glossed over and nobody really cares. And, I'll tell you right now, it's not necessary to know about physical and virtual memory and how they work to understand what the stack and the heap do. But I feel like it's an error to gloss over them because further down the line, it's going to help you so much more as a programmer. So I'm going to go ahead and introduce them, but don't worry, it's going to be fun and it's pretty fascinating stuff actually. So as you probably know, the operating system is doing a heck of a lot of stuff in the background. I mean, you could even just hit you can go into your process monitor on whatever machine you're using, and you can see, in this day and age, there's tons of programs and processes and executable files running in the background in memory at all times, managing things, right? And that's only a little glimpse even of what all the operating system is doing a lot more than that. And only one part of the operating system's job is to manage memory, right? But it's a big job because ultimately a computer is just memory and a processor doing work on that memory. Um, and and when I say memory, I'm not necessarily just talking about RAM. I'm talking about all types of memory, which we'll get into more later. So, physical versus virtual memory. Well, let's first talk about physical memory. So, I'm not sure if you've done it before, but many people have purchased a RAM chip, just physical chip, and it's got, a bunch of it's got a bunch of pins on it, and it fits into a slot on your motherboard or somewhere else on your computer where the RAM is meant to be plugged into, right? DDR3, there's other stuff like there's DIMM slots, SO-DIMM slots, and stuff like that. I'm not a hardware guy. Um, when I was younger, I used to open my computer up and I'd put new video cards in and sound cards in, and I think I installed a new hard drive and mess with the motherboard a bit. I used to do that stuff a lot when I was younger, but I haven't played with hardware in quite some time. So forgive me if I'm a little bit inaccurate on some of the hardware stuff. But we don't even need to go into too much detail on that. But the point is that you have your RAM chip. It plugs into the motherboard, into the computer, and now it's accessible by processor and the circuitry in the computer, right? And but what is this, right? It's just space. It's just space. It's bytes. It's bits and bytes um, of storage. And when I say bits and bytes, it's ultimately bits, yes, but the smallest usable addressable segment of memory is usually a byte. We don't go to the bit level necessarily. We can modify the bits, but we don't address them and deal with them on an individual basis all the time because there's no real point. That's like saying I'm dealing with a parking lot and I'm going to address and deal with like each individual piece of rock inside of the asphalt of the parking lot. It doesn't really make much sense, but it doesn't mean that because the parking lot's made out of parking spaces that it's not ultimately made out of, you know, asphalt and aggregate uh, chunks of rock and stuff like that. So, anyways, so the whole point of this is that the hardware RAM has byte storage and the capability of storing information ultimately as numbers, right? And the operating system has to manage all this because if you think about it, what if I had five programs running and all five programs wanted to use the same segment of physical RAM? Well, now if there's you got a problem. They'd either be stepping on each other, like the four of them wouldn't work and one would. It would just be overwhelming the processor. Like it just wouldn't work out well at all, right? And so what the operating system does to deal with this is all of the memory addresses, as we've seen in our previous videos, all those slots that are all addressed using hexadecimal, like 0x00FF66AA or something like this. All of those slots aren't actual physical RAM slots necessarily. And what I mean by this is that they're an abstraction created by the operating system, and it's also which is also managed by the hardware, by the way, because there's actually a physical piece of hardware called the MMU, the Memory Management Unit. You can look it up on Wikipedia or Google, and you'll see this. And it assists the operating system, and it allows the operating system to do this thing where it's basically taking um, physical areas in RAM. So let's say the RAM is divided up and it has slot A, slot B, slot C, slot D, slot E, and slot F. And then we have the virtual memory, and we're talking about memory address 500, 501, 502, 503, 504, 505, right? Well, what the memory management unit does is it says, okay, well, these virtual memory slots correspond to these physical memory slots in RAM right now. And now let's go ahead and make let's make these virtual memory slots not correspond to these physical memory slots anymore. We'll make these virtual memory slots correspond to these other physical memory slots, which are somewhere else. So it's what they call mapping. It's mapping virtual memory to physical memory. So in a sense, when I tell you that your program is not dealing with physical memory, it's dealing with virtual memory. It is dealing with physical memory, but it's doing it through virtual memory. So in other words, yes, most of the time when you store stuff in your program's memory at all, like when you assign a variable, a number, like when you assign a value to a variable and you're making classes and you're doing all that kind of stuff, yes, it's being stored in physical RAM because that doesn't make sense, right? Like the computer is a physical device, so you can't not store something at all physically on the computer. It doesn't make any sense. It has to be somewhere physically on the computer. Either it's in RAM or it's on the solid state drive or the hard drive, um, but it's being stored somewhere, right? So it's not to say that we're not dealing with physical objects at all, but what it does is it allows the operating system to do some cool stuff in order to maximize the efficiency of the computer and how it's dealing with memory and RAM. So, like I said before, what it will do is it will say, okay, well, this program is loaded into this virtual memory space, and then we're going to load this other program into this virtual memory space below that, and then we're going to load the third one below into this virtual memory space below that. And what could happen is, let's say program one was using physical memory A, B, C, D, E, F, and G, and now program one's closed. So now program two, um, so now program one no longer exists. We only have two and three open, which is like non-existent in today's world. Now we have like 500 programs running in the background. But let's say we only had two. Now what it can do is, let's say it's quicker for some reason to access, um, or it's more efficient for the computers to manage the memory and have it swap so that program two's memory is now in the physical memory area that program one used to be. Or let's say program two just needs more memory and now it needs to grow, and it can grow into the physical memory where program one used to be. Well, by having the program deal only with virtual memory, the program itself doesn't have to keep track of all this crap of where it's actually being stored in physical memory. That's what the operating system is doing through the memory management unit. And that's what's cool about virtual memory. And it also allows something called paging. And so, what paging is let's say we have a parking lot, like I was saying earlier, and this parking lot has 40,000 parking spaces in it, right? Well, let's say you need to tell somebody to go to your car and grab something that you left in the car. You say, hey, John, I parked in lot B, row two, and I have a gold Toyota Prius or something like this, right? Well, lot B, row two, doesn't actually exist physically. It is a concept and an abstraction that the human mind uses to communicate better the location of this parking spot that this car is in. That makes sense, right? And that's what I want you to understand about most of these things that we're talking about in computer science in general, especially dealing with memory and storage. That's actually what they are. In other words, Physically, the computer memory is just a whole bunch of bytes. It's like a field of bytes, and we we apply these labels to these bytes, like parking space, or parking lot, which is a collection of parking spaces, or parking structure, which is a collection of parking lots that might be stacked up on top of each other, right? But at the end of the day, the reality is it's concrete, asphalt, and paint. And that's the same way with computer memory. Okay, it's not concrete, asphalt, and paint, but it is it's chips which are allowing you to store information in the form of numbers. And we refer to this information as bits and bytes in storage. Then we got our kilobytes, our megabytes, our gigabytes, petabytes, and all that stuff more. Excuse me. So the idea here is that the operating system can section off an area of virtual memory and call this a page. And in Windows, it defaults to 4,096 bytes. And I apologize that I don't know off the top of my head what it defaults to, or even if Mac OS and Linux use that exact system, because I'm more familiar with Windows systems programming since I'm doing malware analysis, which most malware, as you probably know, is affecting Windows users. So I haven't done as much study and research in Linux and Mac operating systems, which Mac's really is based off Unix anyway. But in Windows, the default page size is 4,096. Well, what's a page, right? A page. Once again, it's just a label. It's like section A of the parking lot. It's still memory. It's just a way to refer to this chunk of memory. Um, and what happens is when programs get loaded into memory, as we talked about in our previous video, which you could watch if you don't understand, when the program gets loaded into memory or mapped into memory, as it's sometimes called, um, it's done so in these things called pages. So, for example, let's say I have like 50 variables in my program that are storing numbers and strings and information, or information about some objects in my program, right? Well, those may all be in a page. And now let's say the program is running in the background idle, and this person's had their computer on for a long time and they're just not using it at all. Well, RAM is limited, as you probably well know. Especially a few years ago, the computer would start to really slow down to a crawl as you used up more RAM. And a long time ago, the computer could just crash, right? Well, that's because RAM is limited and it's still pretty precious. I mean, we're getting up there to the point now where it's not as big of a concern, but it's still a limited resource. And RAM is used for a particular purpose because it's quick to communicate with for the processor, right? So, in other words, it's not as fast as the processor registers are inside the CPU, but it's pretty fast. It's random access memory. You load the program in, and it puts something in RAM and takes it out, puts another thing in RAM and takes it out, puts another thing takes it out, and all this stuff, right? So you want to in order to have the computer operate in an efficient manner, you want things that are using RAM to be things that are actively being used. You want programs that are using up the most RAM to be the programs that require the most memory and that are actually active and being used. And so the operating system knows this. So what it does is it says, okay, well, this program hasn't been used in 2 hours. So what we're going to do is we're actually going to take this program out of RAM and we're going to put it on the hard drive or on the solid state drive in some cases. But since the program itself is only aware of these virtual memory addresses, because, like I said, the programs never ever deal with physical memory directly. They do it through the operating system. So they only ever see those virtual memory slots. The program doesn't know that whether it's in RAM or whether it's on the hard drive or whether it's on somebody's thumb drive or on a solid state drive or whatever. It just for all it knows, it's still in RAM because it's dealing with these spaces in memory which are loaded in RAM, right, or loaded in memory. But the operating system could put something that you think is in RAM basically on the hard drive or on the solid state drive to free up RAM for other programs and processes that need the RAM at that moment more, because this particular program is not doing anything, it's just idling. So if we were to just let it take up RAM, it's going to make the whole computer run out of RAM quicker, and it's going to slow it down and make things crash and all that. And so that's what it does. And then when that program becomes more active, it then loads that. Um, it basically goes to the solid state drive and it pulls the image, which is basically just it's like taking a screenshot or a snapshot of the program state, and it saves it to the drive. And then when it pulls it, when you make that program active again, it loads it off the drive and it copies the image that was on the drive back into RAM again. But it does this invisibly to the program and to the user. The program has no idea this is happening because the program itself just is dealing with the virtual memory addresses, and because the operating system is able to map those virtual addresses either to the solid state drive or to RAM or to a hard drive somewhere or even to a network drive possibly. The program has no concept of any of this. So that is virtual memory. Virtual memory is the memory that the program has a concept of and is dealing with, but it's not necessarily physical RAM. And then physical RAM has its own separate set of addresses which are mapped, which is like, for each space here, I'm going to match up the space here. So I'm going to map this space to that space to there, maybe this space up here, that space there. It's being mapped, from the virtual memory to the physical memory by the memory management unit, the MMU. Now, how does this help you to understand stack and heap? Well, the reason why this could help you is because it's important to know that the stack and the heap are just data structures. They're just abstractions. They're just concepts, just like a page is in memory, just like a word is or a byte is, right? Just like a parking space is, right? Because a parking space is just asphalt with paint on it. But we don't say, hey, go to that spot over there, or go to that asphalt paint. We say, go to that parking space, right? Well, that's the same way the stack and the heap are. The stack and the heap have to do with virtual memory. The physical memory chip has no concept of the stack and the heap. The processor doesn't even have any concept really of the stack and the heap. Um, it uses it to operate because that's what we designed it to do, but that doesn't mean that it really understands it, or that it's a physical thing. It's not. It's not a physical thing at all. It's nothing but more memory slots that are sectioned off for a particular usage. And we'll go into more detail in the next video on how specifically the stack and the heap work as data structures. I'm sure you may have heard this before, that the stack is a first in, last out. It's like when you stack paper up. Um, you know, it's like when you stack up, like I have a stack of index cards right here, right? So this one goes in first, right? And then or like this one goes down, and then I put one more down. Now, which one comes out first, right? Well, the first one in is the last one out. So the last one is the first one out. And then the first one in is the last one out. So, but that's just a concept. That's just a concept that we use to reason about memory. And in the end, it's all just these bytes and slots in memory, and it's how we're choosing to manage these slots. The keyword there, manage. The operating system is managing memory. We, as programmers, really are also managing memory. The stack and the heap manage memory. But at the end of the day, they are slots, just like parking lots, or just like parking spaces at a parking lot. And we have parking lot section B, we have parking lot section A, we have stack, we have heap. And that's important to understand because let's say there's a better way of doing it too in the future. Maybe the stack and the heap aren't the best way. I mean, not very likely, but it's possible. There may be other data structures that are possibly better data structures for handling some of the things that we do today. So it's cool to understand what these are and not just take them as gospel and like that's it. It has been done. This is all we're ever going to be able to do. The stack and the heap are the computer. That's not how it is at all. And one more thing I wanted to talk about is that, yeah, I mean, you don't go out and you don't buy stack memory and heap memory. You don't go to like Fry's Electronics or Best Buy and say, "Hey, I need 2 more gigabytes of stack or heap," because it's not a physical thing. It's just a an organizational tool that we use to better relate to and reason about memory. So I hope that helps you understand. I talked about one kind of key cool thing that the operating system can do using virtual memory and physical memory and the link between the two. But there's many other things it can do as well. It's a very complicated subject. Some people's entire careers are based around this stuff. And if you think about it, really, the entire computer sciences are based around this stuff because a computer itself is nothing more than memory slots and a processor, which is doing operations on data and moving it to and from those memory slots. So in the next video, we're going to go over detail about stack and heap. I'm going to get the whiteboard back out, do some drawing, and maybe show some code and stuff. But I wanted to explain virtual versus physical memory first because I think it will help down the line, and it's something that a lot of people just don't seem to want to explain. They just take everything for granted, and they just talk about the stack and the heap as if they're just built into the machine or something. Not. All right, guys. Thanks for watching, and take care.